Let us get introduced to maximum likelihood estimation. Our problem is as follows. We are given samples x1 to xn. We assume that they come from a distribution, say parameterized by theta. We know the form of the distribution, but we don't know the parameters associated with the distribution. Our problem is finding those parameters. To be a little bit more clear, so let us look at the problem of estimating the parameters for a one-dimensional data with an assumption that the distribution is normal or Gaussian, univariate. We are given a number of samples and we are asking a question whether this Gaussian or this one, which is the most likely one? The answer is obvious, it is this, because we see more samples in this region and far less samples in these regions. How do you formulate this problem mathematically? The problem is formulated as an optimization problem or a maximization problem where we would like to maximize the likelihood of this set coming from this distribution. Assuming the data samples are independently sampled, so the problem is now max over theta. Theta is the unknown parameters, say mean and variance in this case. Product of I is equal to 1 to n, f of xi given theta. This is usually, these product terms are converted to addition with the help of log. We take a log of this function, which gives you the maximization problem remains maximization and product becomes sum and log of the same function. To understand this a little bit more precisely what happens, let us look at the situation where this function is Gaussian. In this case, the problem will become maximization over mu sigma, I is equal to 1 to n, 1 by sigma root 2 pi e power minus x minus mu by 2 sigma square. And if you take a log, you get max over mu sigma, I is equal to sum I is equal to 1 to n, minus log sigma, minus log 2 pi whole power 1 by 2. What remain only is this term minus x minus mu by 2 sigma square. Now our problem is now we want to find mu and sigma that maximize this term. How do we do that? We use our familiar trick of, say, differentiating with respect to mu and equating to 0. If you differentiate this with respect to mu, this is independent of mu, this does not, this disappear. This is independent of mu, this disappears. What is left out is only this term. So what is left out is sigma I is equal to 1 to n minus 2 into x minus mu by 2 sigma square into minus 1, and this is 0. Or we can write this as I is equal to 1 to n xi minus mu is equal to 0. Or we can write this as mu is nothing but our good old formula that we know is the maximum likelihood estimate. The same thing that we could do for variance or standard deviation. So you can differentiate with respect to sigma and equate to 0. So when you differentiate with respect to sigma and equate to 0, this you get minus 1 by sigma. This term is independent. This term becomes plus 1 by sigma cubed into xi minus mu whole square. If you multiply sigma cubed, and of course we want to equate to 0. Indeed, there is a summation here. N into sigma square plus I is equal to 1 to n xi minus mu whole square is equal to 0, or sigma square is 1 by n I is equal to 1 to n xi minus mu whole square. Of course, this is also our familiar expression. There is nothing new with the final results that we got, surprising for us at this moment. But the lesson for us is, given the samples and the assumption is made on the type of distribution, we can estimate the parameters of the distribution with the help of maximum likelihood technique.